So we're still talking about black holes. And so last time, after talking about the Schwarzschild black hole quite a bit, we got started with our discussion of the Reissner-Nordström black hole. And I didn't finish this off, so I'll do that first. So that, you remember, is a charged version of the Schwarzschild black hole where we throw in some charge inside the black hole, and we pretend that, well, astrophysically we can do that, which we can't really. I mean, matter tends to be neutral, so it's very unlikely that a black hole will naturally acquire a large charge, but as a matter of principle, there's certainly no obstacle in throwing charge down the black hole. And as the charge becomes more significant, the electrostatic field energy that the charge produces, creates a, makes a contribution to the curvature of space-time, and you end up with the Reissner-Nordström solution, which is just a version of the Schwarzschild solution with, with an extra term in the metric. And the extra term, of course, comes with a charge Q. So the charge of the black hole is going to be Q. So now we have a black hole that's characterized by two numbers. It's still spherically symmetric, but it has a mass and a charge. The function f, as we saw before, we can always re-express in terms of a variable mass function. And the variable mass function takes the form of the constant mass that we would measure at infinity, minus the stuff that's left over when we bring the surface, of radius r down to a finite value, leaving out all of this electrostatic field energy outside of that sphere. So that decreases the mass from its original value at infinity to something that corresponds to what you leave out when you consider a sphere of constant value of r. And, and we saw last time that if you differentiate the mass and you associate that with the energy density, you get exactly the usual relationship between the energy density and the square of the electric field. All right, so we talked about that. We talked about the fact that here we have a function f that has two zeros because, if we look for zeros of f, now we have a quadratic equation. So we have two horizons in the space-time given by m plus or minus the square root of m squared minus q squared. And we were just in the middle of talking about that and trying to decide what this means. So what does it mean to have two horizons? In Schwarzschild, of course, we were familiar with the notion of an event horizon. So now we have presumably that plus some other kind of horizon. The outer horizon, the one that comes with a plus sign, goes to 2m in the limit where q goes to 0. But there's another horizon that also, that in the limit where q goes to 0, the inner horizon would go to 0. So that's why we don't have it in Schwarzschild. We get n minus m in Schwarzschild, so we don't get a solution except that r equals 0. Right. So. But, for non-zero q and for a q that, satisfies the bound here that we need to place in order to have real solutions, we have two horizons. So that's a feature that I want to explore. And, one thing that it's going to mean is that, the Reissner-Nordström black hole in its interior is quite a bit richer than the Schwarzschild black hole. In fact, it's pretty weird. And we're going to explore its properties, and I'm going to tell you about, again, how realistic all of this is. All right. So let's look at how particles move in that space-time, and that's going to give us a clue on what these things mean. So I could look at the behavior of charged particles. I won't do that because it's more complicated than I need it to be. If I were looking at the motion of charged particles, I would have to worry about the gravitational attraction of the black hole and the either electrostatic repulsion or attraction of the charge of the black hole, depending on the sign difference between the charge that I'm making move and the charge of the black hole. So when you look at the motion of charged particles, you're not getting geodesic motion because you have the force exerted by the electrostatic field of the black hole on the moving charge. And that force, of course, will depend on the relative sign. Hello, Steve, how are you? That force will depend on the product of the sign of the, whether you have a sign difference between the two charges. Anyway, so we could do that. It's a straightforward exercise. But here I'll just throw in a neutral particle. And if I throw in a neutral particle, there's no direct action of the black hole charge on that particle, but there's still an indirect action because the geometry now has been modified by the charge of the black hole. So the geodesics are going to be taking into account the fact that we have this electrostatic action on the space-time. So let's look at the motion of the particles. I'll stick to the usual coordinates here because I'm not going to worry about t. I want to look at the radial motion of the particle, how r behaves as a function of proper time. So we haven't talked a lot about geodesic motion. We haven't worked out geodesic equations in this course very much, but here's a quick way of doing it. So to get geodesic motion, well, you can get to the metric, you can get the Christoffel symbols, you can write down the usual form of the geodesic equations, and that will give you a set of second-order differential equations. And then you can apply the usual trick of classical mechanics, the usual tricks of classical mechanics, where you try to integrate those equations, taking into account constants of the motion. You can use the Killing vectors, you can do all of this. But the real quick way of doing all of this is to just recognize that this thing is actually a Lagrangian for geodesic motion. So usually we should put a square root on top of this to make it a real proper Lagrangian. But what I'm telling you is that this works, so you don't have to put in the square root if you don't want to. There's a lot of fine print that go into this. I mean, here we're restricting ourselves to a fine parameterization for the geodesic. If we were using the form with the square root, we would have a form that would be reparameterization invariant. So there's some advantages to the square root form. But if you want to get the equations of motion quickly, you just plug in this Lagrangian into the Euler-Lagrange equations, and you're done. And you can use all the tricks of classical mechanics again to identify constants of the motion through, if the Lagrangian doesn't depend on one of the coordinates, then you know that you have a constant of the motion for the usual reasons. So, the claim is that this is a Lagrangian for geodesic motion. And in our case, what I want to look at is a particle that's going to be falling in radially without angular motion. So I'm not going to give it any angular momentum, again, to keep the discussion as simple as possible. So we're going to pick theta dot and phi dot equals 0. I'm going to put the particle in the equatorial plane, so I can get rid of my sine squared theta. And for this kind of motion, then the Lagrangian will reduce to -1/2 f t dot squared plus 1/2 f minus 1 r dot squared, and that's all I have. Numerically, the Lagrangian has to be equal to -1/2 because I'm normalizing my velocity to be a unit velocity vector. So numerically, before after you do the variation, the numerical value of the Lagrangian is equal to -1/2. The half is really not necessary. I could have thrown it out, but because I'm going to apply this to the Euler-Lagrange equations, I'm going to kill the 1/2 by differentiation. So what do you do with this? Well, the first thing you look at is, you plug that into the Euler-Lagrange equations. So for each coordinate that enters here, t and r, you apply the usual procedure. You notice that the Lagrangian doesn't depend on t. So that means that dl dt dot is going to be a constant of the motion. So if you didn't know anything about Killing vectors, you would reproduce the fact that we have a conserved energy here by applying the usual trick of Lagrangian mechanics. that is equal to minus f t dot, and that is what I'll call minus the energy per unit mass. And I'll put that, I'll put the tilde on top to remind ourselves that this is an energy per unit mass. So this is energy per unit rest mass for the particle. And with this, we have an equation of motion for t, which says that t goes like 1 over f. I inserted the minus sign here, of course, to kill this one, to get the result that for E positive, we have, that time proceeds, that motion proceeds forward in t. And here we get the usual, problem at f equals 0. So that tells us once more that the behavior of t is strange and pathological at the event horizon. I'm not going to be concerned about that. I'm going to bypass this difficulty in just a second. I could do the same thing for r dot, and I would obtain a second order differential equation by substituting the Lagrangian into the Euler-Lagrange equation. But here we have a conserved quantity, so I'll take that to my advantage. And in classical mechanics, what we would do is to get the second order differential equation. We will multiply r dot dot by r dot. So all the terms in the equation we would multiply by r dot. That's what I call the r dot trick. And then you would integrate once, and you would get an energy equation for r dot squared. That's what we always do in classical mechanics to get a first order form for the equations of motion. Here, I can just plug that into the Lagrangian and recall that it's numerically equal to minus a half, and get my first order equation directly like this. So the next step is to say that minus 1, I'm going to now get rid of the 1/2 because I don't need it anymore. So minus 1 is going to be equal to minus f times t dot, but now t dot stands for E tilde squared over f squared. And here we have r dot squared over f, and we can solve for r dot squared. So here we have a 1 over f factor that's common to both factors. So we have r dot squared. I'm going to throw this over to this side. I'm going to get a plus 1 multiplied by f. And I'm going to throw that over to the other side, and I've multiplied by f. So I get E tilde squared. So that's my energy equation for the radial coordinate. And I get this very directly by just making the substitution for t dot and using the normalization condition on the velocity vector. So really very little effort is required when you do it like this. You could do it with a killing vector. That would be exactly the same calculation. So you would get this guy here by appealing to the killing vector. You would get this, and then you could substitute that into the normalization condition for the velocity. That would be exactly the same thing. So whether or not you want to do this with a Lagrangian is up to you, but in any case, we'll end up with this equation. So the meaning of this equation is pretty clear. So this is something like kinetic energy for the particle going in. This will be like potential energy, and that's the conserved relativistic energy. That's why there's a square. But the meaning of this equation, or the interpretation of this equation, is the same as what we would get in classical mechanics. And what we do in classical mechanics is that we plot the potential energy, and we draw a line of constant energy, and we see where the possible motions can occur. So if I do that, if I plot the potential energy, meaning I plot f as a function of r, well, I look at my f up here, and I know that it's going to change sign twice. So it's going to start from an asymptotic value of 1 at infinity, and it's going to decrease from that. It's going to cross 0 once, but it's going to cross 0 again. And for r nearing 0, it's going to go up to plus infinity, because for small r, it's the q term that wins, and that's positive. So it goes up to plus infinity when r goes to infinity, when r goes to 0. And it goes to 1 when r goes to infinity. It crosses 0 once at r plus. It crosses 0 again at r minus. If we were dealing with a Schwarzschild black hole, of course, all of this carries over. The main difference is that f would only change sign once. So you would change sign here at r equals 2m, and then it would keep going down and down. But as r goes to 0, it would go down toward minus infinity instead of plus infinity. So the new feature in Reisner and Nordstrom is that the shape of the function is very different. Okay, so that's the potential energy. Now we draw a line of constant energy on top of this. And we know that the motion can occur only when the difference between the total energy and the potential energy is positive, right? So the difference here has to remain positive. We see the difference goes to 0 over here, so that we can only get motion on the right of that turning point. And that's the place where r dot goes to 0, because that's the place where potential energy becomes equal to the total energy, well, squared in this case. So interestingly, we have a turning point. And now we have to think about this. So one thing to remember is that when f changes sign, the meaning of r and the meaning of t become altered. At least the meaning of r become altered. We know that t is suspect. We don't want to, pay too much attention to it. So let's focus on r. When f is positive, r is clearly recognized as a space-like coordinate, right? So, and if you're moving in a region where f is positive, you're moving outside the black hole, you can move either inward or outward. There's no obstacle in moving in any space-like direction. When f becomes negative, r becomes recognized as a time-like coordinate. When f changes sign, r has to move in one specific direction. And when, after you've crossed the event horizon, r must proceed toward negative values. Because it's proceeding toward negative values, that has the meaning of moving forward in time. T, of course, doesn't mean time anymore inside the black hole. But f will change sign again, which means that r will reacquire its meaning as a space-like coordinate. So presumably inside the inner horizon, f is positive again, and r reacquires its meaning as a space-like coordinate. And presumably inside the inner horizon, there's no obstacle in either moving in or out. That's exactly what we see. So here we're talking, say, about a particle that moves in. So initially it's moving in. It could decide to go back if it wanted to, but we're not letting it. We're letting it just free fall toward the black hole. It will cross the outer horizon. And at this point, it has no choice. And the geodesic motion predicts that it will just keep on going in that direction. And while it does that, it just moves forward in time inside the black hole. If we were inside a Schwarzschild black hole, the function would never change sign again, and the motion would proceed toward the singularity. And that's what we would expect for a Schwarzschild black hole. But here, we have another zero crossing here. The function f changes sign here. And as the particle moves beyond this point, r becomes space-like again, and now there's a chance for the particle to turn around, because it's possible to move in or it's possible to move out when r is no longer, a time-like direction. And sure enough, we see that according to the equations of motion, there will be a turning point. After meeting the turning point, the particle starts, moving out again. It crosses the inner horizon again, but now it's moving out. As it crosses the inner horizon again, f has changed sign again, right? And r has become, again, a time-like coordinate. But you're moving out, so you have to keep on moving out if you're going to keep working, moving forward in time. So now you emerge out of the inner horizon. You keep on going until you hit the outer horizon again. And now f changes sign again, but you keep moving out, so you've come out of the black hole. So there's something pretty funny about this. So if you go inside a Schwarzschild, if you go inside a Schwarzschild black hole, you will go to the singularity. If you go inside a Reisner-Nordstrom black hole, you will meet a turning point at some small radius beyond the inner horizon, and then you'll turn around and you'll come out of the black hole again. That seems funny. That seems counterintuitive. That seems counter to what we think we know about black holes, but it's true. A couple of things before I bring you more information, because this is purely a spatial representation of what's going on. We have to think about how it unfolds in time. Time meaning something that's appropriate, like a regularized version of the time coordinate or something like that. But one thing we could ask is, why do we have a turning point to begin with? I mean, what's the physics there? So in Newtonian mechanics, we're pretty used to encountering potential barriers. And in fact, the typical Newtonian potential will have a potential well, that is then, followed by a potential barrier. So we're used to seeing potential barriers in classical mechanics. But when you think about this, those potential barriers are always associated with angular momentum. You never reach the center because angular momentum protects you from reaching the center. So basically, with angular momentum, you always go around. You never can actually penetrate and go toward the center. Here, there's no angular momentum. I turned it off. So we have a particle falling in radially, and there's no angular momentum to protect it. It should go toward the center because, it never deviates in direction. And yet it doesn't. It never reaches r equals 0 because the turning point here always prevents it from doing that. R equals 0 is a singularity. We still have a singularity of the spacetime at r equals 0 that's seen pretty clearly from the metric. It would be seen very clearly if you were to look at the Riemann tensor or things like that. So there's still an r equals 0 in the spacetime. There's still a singularity there, but particles falling toward the black hole with no angular momentum, just proceeding radially toward the black hole, never have a chance to get there. So all of this is pretty peculiar. The only way you can make sense of all this is to try to draw what's going on in a spacetime diagram. And that would require, for example, constructing Kruskal extensions to basically be able to eliminate the coordinate singularity at each crossing f equals 0. Because the problems with T that we've encountered in Schwarzschild that had to do with the 0 crossing of f will occur each time you have a 0 crossing in f. But now you have a lot more. You have, at least following this guy, we have one 0 crossing on the way in, another one here on the way out, and another one here on the way out. So now you have multiple copies, it seems, of horizons, which will require multiple constructions of Kruskal coordinates across each one. And the key point is multiple copies. So with Kruskal extensions, we're used to the fact that we have copies of everything. Each surface r equal constant is copied twice in Schwarzschild. Here we're going to see that, in fact, it's copied a multiple number of times. In fact, it's copied an infinite number of times because of the addition of charge. So what I'm going to do, in the book, I flesh this out a lot more, and I go through the construction step by step, and I give you, Kruskal coordinates for the outer horizon, Kruskal coordinates for the inner horizon, and I go through the thought experiment of moving in and going from one Kruskal patch to another Kruskal patch, and yet another Kruskal patch, and then another Kruskal patch. So it's a very involved story. What I'll do, instead of retracing all of this, I'll just draw a space-time diagram. It's going to be a Penrose-Carter diagram of the same kind we saw last time for Schwarzschild, but now it's going to be the Penrose diagram for Reissner and Nordstrom. And I'm going to draw it, and then I'm going to explain how all of this is depicted in that diagram. And I think gradually things will start making sense. Okay, so the Penrose diagram for Reissner and Nordstrom looks something like this. So I'm going to draw two lines like this that will represent the r equals 0 singularity. And what you see here is that on a space-time diagram, these will look like time-like regions. The singularity is time-like in each case. And that has to be because r equals 0 lives in the region where f is positive. And where f is positive, r is space-like. Therefore, r equals 0 has to represent a place in space, not a moment in time. So the nature of the singularity has to be very different here from what it was in Schwarzschild because of the second 0 crossing. I'm going to draw a diagonal line like this, and another one like this. I'm going to draw two lines like this. And there would be another set of lines like this. This one I'll extend like this. Extend this one like that. This one I made it a bit too long. I'm going to extend it like this. Extend it like that. This. And let me stop here for the time being. It's not done, but let's keep it at that. Okay. This is where we start. This is our universe over here. This diamond over here is our universe. This we recognize as the diamond that was outside the Schwarzschild black hole in the previous Carter diagram. So just to remind ourselves, for Schwarzschild, we had a Penrose diagram that looked like this. So this diamond over here is pretty much the same one I have here. So here, as in Schwarzschild, we're going to have Scri plus. Here we're going to have Scri minus. This would be, I0. This would be I plus. So all the same labels apply here. But here we have the first horizon. In Schwarzschild, it would be 2m. This is R plus. The outer horizon that has all the same properties that R equals 2m has in Schwarzschild, it has also, it acts as an event horizon and all of this stuff. In Schwarzschild, we had one copy here and another copy there, so that's the same is true over here. And those are my two copies for I plus, and well, this one extends over here, and so on and so forth, and this one, of course, extends inside the black hole. So this, this is the extension of R equals 2m, and we have the same thing over here. Well, R plus is a null surface. R minus is a null surface for the same reason, because when f goes to 0, we have that R equal constant becomes a null surface. You remember that? So the gradient of R becomes a null vector when f goes to 0. So on our diagram, we have this over here that gives a representation for the inner horizon. So we have those lines here. Those lines here are lines of constant R when R is equal to R minus. The curly line over here is R equals 0. But it doesn't stop there. This is another null surface, and it corresponds to another copy of R plus. We already had multiple copies. We had copy number 1, copy number 2. We get copy number 3 over here, copy number 4 over here. We have another copy of Scri minus up here. And if I were to, extend it like this, I would have another copy of Scri plus over here. So it just keeps on going. This is another copy of Scri minus. This is another copy of Scri plus. And in fact, it will extend to the past as well. I'll talk about that in just a few seconds. This is my other copy of Scri plus, my other copy of Scri minus. So, again, to establish that this is the right causal structure for Rice and Nordstrom requires quite a bit of work, and I do the work in the book, so you can follow the discussion there. But at least as far as what we should have in the space-time, I think it makes sense. So we have two horizons, so it makes sense that we should have two sets of null surfaces, labeled by constant values of R, R plus, and R minus. So we have those, and we still have to come to grips with the fact that we just don't have, it's not enough to have just two copies of everything. We have multiple copies of everything. So we have two copies here for R plus, we have two copies here for R minus, but then we have the repeated copies over here. We have Scri plus, we have Scri minus, so that we expect to have. R equals 0, as I said, we expect to see as a time-like singularity, not a space-like singularity like in Schwarzschild, so that makes sense. And basically, at least there's no contradiction with anything that we might imagine. Now let's think of that observer. So I want to depict the motion of that observer, and we see that the motion in the space-time diagram will match what we were thinking about just before. So the observer will start somewhere at a finite distance outside the black hole. So the observer will start, say, over here. And the first thing the observer does is to cross the event horizon. So moving on a time-like trajectory, the observer crosses the outer horizon. Then the observer keeps on going as it, after crossing the event horizon, there's no other choice. The observer has to proceed toward smaller values of r, so he has to proceed toward the inner horizon, and the observer crosses the inner horizon. Then there's a turning point. It just occurred to me that I didn't finish my story about the turning point. I'll come back to that in a second. So then there's a turning point. So the motion turns around here. And we see it here because we see the observer crossing the inner horizon and crossing again the inner horizon. Here, r was decreasing for a while, but it started increasing so that we go towards smaller values of r and then larger values of r, and we cross again the inner horizon. Over here, we could not distinguish the two copies of the inner horizon. And it looked as if the particle was just moving in and then out again. But in space-time, we see something different from that. We see that the observer moves in, and then it moves out again, but he goes through a different copy of the inner horizon. The observer keeps on moving forward in time as depicted in this diagram.
Can you distinguish between which r minus line it's going through? And is it necessarily only one, or do other parameters affect which one it goes through?
So this one as opposed to this one?
Yeah.
So it requires a little bit of work. But yeah, you can actually show that for positive E, the motion is like this. It goes on the left of this point. But for our purposes here, it doesn't make a big difference. But yeah, that's just an outcome of doing more work and trying to figure exactly where the motion is going. So in principle, non-geodesic motion could proceed through, over here. And it doesn't really change the story very much. But yeah, you can take my word that for geodesic motion, for positive energy, that's where the particle goes. Okay, so the particle keeps on going. So after crossing the inner horizon once more here, r has become time-like again. But now the time direction related to r is forward. So r has to keep on moving forward. There's no way that the observer could come back and recross r minus, because according to the space-time diagram, this motion always has to proceed within the light cones. So the particle proceeds, or the observer proceeds toward r plus again. That's the second crossing of r plus, but now we recognize that it's a very different copy. It has nothing to do with this one. It's a totally different copy of r plus. And the particle comes out. And now the observer is outside the black hole, but into a different copy of the external universe, right? So now we have the r corner of the universe, which is over here. We have a black hole tunnel, and now we have another copy of an external universe that we can access if only we were to be brave enough and travel within the black hole. So that's what this was trying to tell us, but now we have more information because we have the time aspect to this. And if you want to be fully convinced of this, you have to go through the work of representing the motion on a space-time diagram using Kruskal coordinates or using a patch of Eddington-Finkelstein coordinates. You can patch this up in multiple patches of Eddington-Finkelstein coordinates, and you can really convince yourself, as I tried to do in the book, that this is really the way it goes. And yes, there's another copy of the universe over here, which looks identical to where the observer started from, and that's that's the full weirdness of the solution, that it gives you way more than you bargained for, right? It was already weird for Schwarzschild because in Schwarzschild we were given another copy of an external universe over here. But we said, okay, well, it doesn't really matter because this would be inside the collapsing star anyway, so it doesn't really exist as a physical thing. And even if it did exist, it would be completely inaccessible because as you try to, there's no way that you can travel from here to there without moving faster than the speed of light. So this, was basically a mathematical construct. But here, I mean, we can actually think of a physical process in Reissner-Nordström that would take you from this universe to that universe. And you have to consider the copy very seriously. You have to consider the existence of that copy very seriously, at least as far as you believe the integrity of the exact solution. So if you believe that your actual space-time is described by Reissner-Nordström, you have to take the existence of those black hole tunnels and those other external universes very seriously. In fact, once the observer is here, the observer sees another black hole lying in the future. And he could choose to go in and go through the tunnel once again and emerge into a third copy of the external universe. So this keeps on going toward the future because, there's another black hole up here that I'm not depicting here because I ran out of space. But the observer emerging here will see another event horizon in the future, and we'll see another black hole in the future, and could choose to repeat the process once more. And we'll go through another black hole tunnel, we'll reemerge again, we'll go through again, and that could keep on going indefinitely. So you can imagine that this whole thing here repeats indefinitely in the future and to the past, because the observer could have emerged from this horizon and decided to go through once more, right? So the whole thing repeats to the past, repeats to the future, any number of times. So we thought we had one black hole. In fact, we have an infinite number of black holes, all stacked up in the future in that one exact solution. So if you think it's weird, you're right. If you're suspecting that maybe there's something fishy going on, you're also right. And I'm going to try to explain what. Any questions before we move on? Yep.
Just trying to understand how these diagrams work as well. Light always goes in 45-degree angles.
Yep.
Is there any restriction saying that it can't zigzag through? Like, can light go through? Or does it have to hit the singularity?
Light, yeah, so if you move purely in radial directions, light will proceed toward the singularity. So there's no obstacle for light to actually hit the singularity. But if you give it angular momentum, then you create a potential barrier for light. And in fact, there will be a turning point as well, and a light ray will just bounce back like this. Okay. So qualitatively, the motion of light with angular momentum is the same as this observer here without angular momentum.
Okay, but so without angular momentum, like the solution, light can't actually go through?
Sorry, I give light angular momentum.
You give light angular momentum.
Not the space-time, not the solution. So it's the same solution, but instead of talking about a test photon that will move in radially, I just give it a little bit of angular momentum, an impact parameter. Yeah. Okay. That's fine. Yeah, so light proceeds in exactly the same way. One thing I haven't talked about is where the collapsing star is going to be in this situation. If we were to let the black hole be formed by gravitational collapse, I'll come to that in a second, but it doesn't destroy this picture. But something will destroy this picture, and I'll talk about it in a couple of minutes too. Ryan, you had a question?
Well, it was just about the stars.
Right. So I'll put the star in a second. Before I do that, I want to go back to my story about the turning point. Somehow I distracted myself, and I forgot to give you the punchline on this. In Newtonian physics, we're used to having turning points created by angular momentum. So it's angular momentum that protects, a falling particle from reaching the center. Here, this observer doesn't have any angular momentum, so there has to be something else that's protecting the observer from reaching the center. The center, well, by center I really mean r equals 0. It's a singularity. It ought to be extraordinarily attractive, yet it doesn't seem to be attractive. It seems, in fact, to be repulsive, because in order to produce a turning point, you have to have a force that turns the particle around. So basically, you turn gravity into an attractive force, and you turn it from being an attractive force to being a repulsive force. That's you need a repulsion to create that turning point. So now you're thinking, well, I know that electrostatically I can produce a repulsive force. If I were a charged particle and I had my charge had the same sign as the black hole, then there would be an electrostatic repulsion. going on. But that's not what we're talking about. My particle doesn't have a charge, and it doesn't feel the direct action of the electrostatic field created by the black hole. So the origin of the repulsion here cannot be electrostatic. It cannot be electromagnetic. Well, if it can't be electrostatic, and there's only gravity going on here, it has to be gravity. Right? Gravity has to produce a repulsion, because that's all we've got. And that's actually the right answer. Think of this mass over here. This is the mass felt by an observer inside a radius of constant r. If you're imprudent enough to let r be so small, there's a chance that this negative sign here will overthrow the positivity of the total mass. So as r becomes smaller enough, it's possible for this negative sign, well, for this term to overthrow this term, and for the effective mass inside radius r to become negative. So inside the inner horizon, and you can work out the algebra, inside r minus, m of r, you have to be within r minus, so it doesn't occur immediately at r minus, but inside r minus, it's positive for the mass function to become negative. And if you have a negative, effective mass, well, you have, a repulsive effective gravity created by that mass. And that's what's going on. There's a repulsion going on, all right, but it's a gravity-induced repulsion, and it's explained very easily, I think, in terms of that negative mass. So by the time you've reached such small spheres, you've excluded so much electrostatic energy that the total gravitating mass has become negative. Yep?
Does this break energy conditions then?
That's an interesting question.
What was the question?
Are we breaking the energy conditions inside the black hole? The only thing that contributes to the energy condition is the electrostatic field energy, and that's still always positive. Yet, the effective gravitating mass is negative, so we're not breaking the energy conditions.
It seems like we're breaking the focusing theorem.
Yeah, so there's something funny going on with the focusing theorem. And I'm afraid I don't have a resolution to that one. So yeah, so if you consider congruence of observers like this, it certainly does seem as if a converging congruence is turning into a diverging congruence at this turning point. And if we're not breaking the energy conditions, something was going to be going on to explain that apparent failure of the Ricciardo-Rees equation to enforce the focusing theorem. I think the resolution is probably to the fact that it's going to be very difficult to arrange for the congruence to be hypersurface orthogonal in this case. And in fact, for light rays, it would be easier to enforce the hypersurface orthogonality condition, but you can't do that unless if you have any angular momentum. So those photons that fall in with a little bit of angular momentum to ensure that they bounce around here are not hypersurface orthogonal. That congruence is not hypersurface orthogonal. So we don't break the focusing theorem because we have this extra term coming from the rotation that we don't kill off. So I think that's the way it goes, that, that in all of those cases, these congruences are actually rotating. And it's the rotation that basically gives a way out of the focusing theorem. So it's not the energy conditions, that's for sure. So I think that's probably what's going on, but I never worked out the details of this. But I think it would be interesting to do that because, I get worried about this, on a regular basis, and but I guess I haven't been worried enough to compel me to actually do something about it, which is, well, not good enough anyway. But yeah, it's a very interesting question. Anything more? Okay, so let me do this again, but now we're going to put the star in, and then I'll explain what's weird about this and why we can expect that it's not physically realistic. And it has nothing to do with the star. So I'm going to put the star in, and it won't change the story. So with star, so let me draw the diagram again. but I'll cut it off a little bit earlier here. So I'll draw the diagram in its original form, and then I'll put in the star as a second step. So we have that, we have that, we have this. And then in principle, we would have another singularity in the past, like this, and so on and so forth. So this is cry plus, this is cry minus, this is r plus, this is r minus, this is still r equals 0. If I want to put the star in, well, I can remember what we did for the Schwarzschild case. In the Schwarzschild case, we said, well, a star is going to start at t equals minus infinity. It's going to move on a constant r trajectory for a while until it runs out of fuel, starts undergoing gravitational collapse. So it's moving sort of like this for a while, and then it goes in, and then it moves in all the way toward the singularity. So anything that's on the left of the collapsing surface, there's matter there, so the Schwarzschild solution doesn't apply. The Schwarzschild solution only applies inside. So basically, we cut all of this off, and we say that, well, the actual Penrose diagram for the Schwarzschild case looks more like this. Now I've made it a mess, I'll do it again. So we have the center of the star, we have the collapsing surface, we have the singularity, we have the event horizon, and it looks like this for a black hole that comes from gravitational collapse. So the basic idea here is that we just need to think about what the star is going to be doing and draw the line that represents its surface, and then we cut off everything on the left-hand side of this. So the star will start again, at t minus infinity. It's going to be a nice regular r equal constant surface, so it's going to move somewhere like this. And then at some point, it starts undergoing gravitational collapse. So now the star, of course, has to be charged. So the stellar matter here has charge, because that's how we give our black hole the charge. As it collapses, the matter itself will certainly suffer electrostatic repulsion, because we give it a total net charge. As it falls in, the shells outside will feel the shells inside through their charge, and there'll be electrostatic repulsion. But here's a case where gravity still wins, at least for a while, and the star still undergoes gravitational collapse in spite of its charge. And it first goes inside the event horizon. And then, well, the details of how charge and mass balance each other out will matter, and the surface of the collapsing star will bounce. It will bounce either because charge is not very effective at producing the bounce, but gravity is, so it will bounce for the same reason we saw before, or it will bounce because of electrostatic repulsion. So that could occur outside the event horizon, in which case there would be no black hole, but if a black hole forms, it could occur either before you cross the inner horizon. Well, it could occur, well, let me just draw it like this. It will occur for one reason or another, so there will be a bounce either on this, well, let me draw it here just to make a difference. It will, so there will be a bounce. Okay, yeah, so sorry, I was forgetting a detail here. So once the stellar surface has crossed the event horizon, there's no way that it can turn around again, right? So it has to proceed forward in time, which means that it has to proceed smaller in r until the other horizon is crossed. And it's only then that the bounce could occur. So a bounce could not occur before that happens. And then it could happen after after the crossing here. It could happen either for gravitational reasons or for electrostatic reasons. That's what I was trying to say. So the bounce could occur here. It could occur on the other side. It doesn't matter. And then the star also, like the observer before, will reemerge out of the black hole at some point. So now the star, what does it? So anything to the left of that surface is inside the matter, so it doesn't, the left of the diagram becomes irrelevant to that because we're inside the matter. It doesn't apply to Reissner-Nordstrom. So we cut this off. So all of the stuff that was on the right is now cut off. And what we have to replace it with here is a regular center inside the matter that will connect to the origin of the star over here. So we can imagine that this is r equals 0, the center. We have the stellar surface over here. Here we have the formation of the event horizon. Here we have the formation of the inner horizon. Here we have the continuation of the inner horizon as a null surface inside the matter. But the point is that anything on the right survives. And what survives on the right is, well, this copy of the event horizon, this copy of the inner horizon, this other copy of the inner horizon, and then there's going to be another copy over here of the outer horizon, another copy of Scri plus, and pretty much all the rest of it. So the star does pretty much, except for details, what the observer over here was doing. It goes through both horizons, it bounces, it reemerges, and then it will presumably keep on expanding forever, or it could choose to recontract and form another black hole and keep on recycling like this forever and ever, and we get the same sort of continuation toward the future. We've truncated the past, because here we decided that the star will begin as a regular star at t minus infinity, but the repetitions in the future can keep on going. Yep.
So there are parameters that control whether it bounces out again to infinity or then starts to recollapse, and could it bounce a finite number of times and then eventually just expand?
Yeah, I think so. So I think the details of the collapse will depend on the details of the mass distribution inside the star, the details of the charge distribution inside the star. And I know there's some people who have investigated these things to come up with models, and you give this profile, you give that profile for the charge, this profile for the mass, that profile for the charge, and you see what happens. And so you can play around, and I think there's a lot of latitude there that I think you can produce whatever solution you want. I don't remember the details of this, and I don't even remember who did that and when, but it's probably been done. Yeah. So whether it continues to expand or chooses to recollapse at some point will depend on all the details. It will depend on the balance between electrostatic repulsion and gravitational attraction within the matter itself. And to describe this requires a lot of details. So it can be pretty complicated. So in spherical symmetry, it's not too bad. So you just have a bunch of independent shells that you can follow, but still you end up with a fairly formidable set of differential equations to describe the fluid. And I think people have done quite a bit of work on self-similar collapse. I remember Tzvi Piran doing this in the 80s and things like that. So there's certainly some literature on seeing what you could expect realistically the star to do in this situation. But qualitatively speaking, there's not a big difference between what the observer was doing and what the spherical star is doing. And if you consider a later observer after the star has collapsed, a later observer can still proceed through all the same steps as our previous observers, and that observer still has this this ability to penetrate the black hole tunnel and reemerge into a new copy of the universe at some later time. So you can ask, well, okay, how long does it take? None of this would make any sense if, for example, there were time distortions going on in the space-time that made this strip, for example, infinite in proper time. But if you think about this, you find that, well, it doesn't happen because you would only get infinite time distortions in terms of proper time if there were if this would go singular somewhere in the motion. But it doesn't go singular anywhere. It's a very smooth thing, and the solution for r as a function of proper time is going to be perfectly finite. So, conclusion is, the time scale required to go from r plus to r minus is always going to be of order m. Of order r plus itself. In fact, it's going to be the light crossing time across the black hole horizon. So that's going to be a few m's. That's going to be a few more m's. That's going to be a few more m's. So basically, in a few m's, you'll have succeeded in going through the black hole tunnel. So if you imagine that you have a billion solar mass black hole, something like this, something that would protect you against tidal forces. So a billion solar mass black hole translates in a time scale of minutes. So this trip would take you a few minutes to complete, and you'd be home free in a new universe after a few minutes' time. So that doesn't stop anything, and then we're still scratching our heads. Is this really possible? Is there something more going on that we're sort of neglecting here that would make this situation highly implausible or perhaps even completely unphysical? Well, let's go a little bit more deeply into this. I'm going to redraw the diagram again and now feature something pretty interesting about the causal structure of this thing. And I should mention that this gives me great joy to do because that was my, the topic of my PhD. So here I'm recreating all the anguish that I had at the time to try to understand what was going on here. Okay, another copy of the Penrose diagram. Okay, I'm going to stick with this. So this is R plus, this is R minus, as usual, and this is R equals 0 as usual. This is cry plus. Okay, suppose that I decide I'm going to make the trip down. So here I go. And as far as I'm concerned, my trip takes, a few minutes to complete if we're dealing with a billion solar mass black hole. Suppose that you decide, well, I'm going to be lonely down there. You're going to keep me company by sending me, Christmas cards every year. Well, instead of Christmas cards, let it be just light signals. So every year on a day chosen by you, you're going to flash a laser beam at me just to say hello. So you're sitting very safely out here, and for the purpose of this argument, I'm going to assume that you're going to keep on living forever. So you're a time-like observer outside the black hole, and you keep on living forever. So you have a trajectory like this, an R equal constant trajectory that ends up right here at I plus. Every year, you shine a laser beam at me. So here's the first laser beam that you shine at me to say hello. Here it goes. That's year 1, year 2, year 3, year 4. And you keep doing this every year. But remember the spatial distortions we've introduced in the Penrose map. As you proceed toward t equals infinity, as you keep on living forever, those light rays are going to come closer and closer together, even though you still, in terms of your time, emit them every year at a regular space interval. It's just that the number of light rays that you can emit in an infinite time will end up being infinite. Right? So all the light rays that you emit in an infinite time will accumulate, and they will pile up more and more and more and more. And they all pile up before the inner horizon. And the last one you emit at t equals infinity is one that just hugs over here the inner horizon. Now, you thought you were being nice to me by saying hello once a year. As I cross the inner horizon up here, in a few seconds, I receive all of your light signals that you've emitted for an infinite time. Each one might have a very small amount of energy, but I'm receiving all of this in a fraction of a second. And you've emitted basically a lot of, we can fine-tune things in such a way that you make sure that you send a finite amount of energy So each time you send me a new photon, it's going to be a photon with a little bit less energy, so that the infinite integration of all of this is not going to produce a negative, an influx of infinite energy into the black hole. So we can make sure that the total amount of energy here is finite. But the energy density that I received, the energy that I received per unit time, is going to be infinite, because all of those signals here, even though they come at decreasingly amounts, with decreasing amounts of energy, they all pile up, and I receive it all at once as I'm crossing the inner horizon. So that's one fact that causes some worry. The other thing that's pretty remarkable about this is that if you send me news about what's going to happen for the rest of your life as you keep on living forever, I'm going to receive all of that news in one flash over here. So all of what's going to happen in the external universe for an infinite time, I receive in compressed form at one instant. Because that's the causal structure that we're dealing with here. The causal structure of the exact Reissner-Nordström solution is such that an observer crossing the inner horizon on this side is in causal contact with everything that's happened in the external universe for all times. And that's weird. When you put in the details in here, and you say, OK, let's think of a physical process. Here it's still contrived, because we're still talking about those light rays that are being emitted. If you insist that the total energy should be finite, and if you do this with a reasonable fall-off condition or something reasonable, you find by working through the details, because of the blue shift effect that we've just revealed here, you find that, in fact, the energy density as measured by the crossing observer goes to infinity as r equals r minus. So anyway, so you come up with a very gentle condition to ensure that you don't send an infinite total amount of energy inside the black hole from the outside, and it doesn't. So unless so if you do it in a reasonable way, you find that this in fact will win. So this piling up effect will win, and you'll find that this observer will see an infinite amount of energy crossing. And that requires a lot more thinking, because if it's true that the energy density as measured by this observer is infinite, you have to wonder, doesn't that energy gravitate? Doesn't it have effects on the internal structure of the black hole that were not taken into account in the exact Reissner-Nordström solution? So basically, the back reaction leads to a very different structure. So a radical, I would say, a radical revision of the internal structure. In more physical terms, what's really happening is this. So remember that, so a black hole, when a black hole forms, it doesn't form necessarily from a purely spherical progenitor. So there will be bumps, there will be deviations from spherical symmetry, and remember that those bumps get radiated away by gravitational radiation as collapse proceeds, and it's this radiation that allows the relaxation to a Schwarzschild state in this case, or a Reissner-Nordström state in this case. In this case, we're talking about a progenitor that presumably will again be a little bit deformed away from spherical symmetry, and the deformations in the charge and the deformations of the mass will lead to emissions of gravitational radiation, but also electromagnetic radiation. So if you put in the smallest amount of deviation, so if you perturb the spherical state ever so slightly, and you follow the collapse, you find that there will be radiation emitted outwards by the collapsing star. That radiation will start interacting with the space-time curvature outside the star, outside the black hole, and part of that radiation, of course, will escape to infinity. But part of that radiation will, in fact, be scattered back in toward the black hole. If you work out this process in some detail, and it requires quite a bit of analysis, you find that, of course, externally, the amount of radiation produced is very small. It's very, it's very small. It's a very slight perturbation. Internally, the backscattered radiation piles up in exactly the same way that your light signals were piling up before. That blue shift effect, that piling up effect that we see on the inner horizon, operates again, but now it's a more physically realistic context. So this backscattered radiation falls in, piles up on the inner horizon. It interacts with the continued emission of outgoing radiation, and through this interaction, you find that, well, the back reaction becomes very large. You have to take into account. And that's just a statement that we started out with a pure Reissner-Nordström solution. It's an approximation even outside because of the small perturbation that we have to imagine is there, those slight disturbances away from spherical symmetry. But it's still a very good approximation outside because everywhere outside the perturbation is very small. But the perturbation inside doesn't stay small. It grows. The Reissner-Nordström solution is unstable to external perturbations. This piling up and the outgoing radiation over here is such that, in fact, the structure of spacetime is radically different over here than it would be as predicted by the Reissner-Nordström solution. The actual solution to the Einstein field equations, after taking into account the perturbation and recognizing that the perturbation grows, is such that, in fact, what you produce is a singularity right here. That spacetime goes singular. But it doesn't go singular here. It actually goes singular right on where you thought the inner horizon was. And it's that singularity that's going to stop you from proceeding beyond there. That's going to stop you from going through the black hole tunnel. And it's that singularity that's going to stop space-time and prevent it from, having other universes to the future and all of that stuff. So that singularity has a different character from the R equals 0 type singularity that we knew about in the case of Schwarzschild or pure Reissner-Nordström. That singularity, so this produces a singularity. The singularity is not produced by this because this is a place where R goes to 0. In fact, R is still finite there. R is still equal to R minus. But what's going on instead is that, well, you have all this mass that comes from all of this, blue shifted radiation. This infinite energy density produces a finite, an infinite mass. So the singularity is an M of R goes to infinity situation, while R itself goes to a finite value. To get a singularity, you need M over R cubed to be infinite somehow. Typically, M would be finite and R would go to 0. That does the job. But if R decides to stay finite, you can still produce a singularity by letting M go to infinity, and that's what this process does. And, well, I'm proud to say that it's Werner Israel and I who came up with this. The instability of the inner horizon was known for a long time, but no one had really worked out a plausible back reaction analysis of this, and we showed that with back reaction, we get a null singularity. That was a little bit surprising at the time because people would have expected a singularity that would be more like Schwarzschild, more space-like than null, but we could show, of course, it's always, Steve will tell us, Steve will tell us that it's always a little bit troubling to discuss singularities and the causal structure of singularities, because singularities are always beyond your manifold. They're always outside of your manifold. But, by looking at a singularity through limiting procedures and things like that, we pretty much convince ourselves that it really has a null character, not a space-like character, and certainly not a time-like character. So, and we called it the mass inflation singularity because it really corresponds to, the mass just expanding beyond any bounds. Externally, you don't see any sign of this. As I said, externally, you don't see any sign that there's all of this going on inside. The perturbation is always very slight. The mass of the black hole will increase a little bit because of this radiation, well, depends how you compare things, but the mass of the black hole outside will be more or less the same as it always was. But the mass, as measured inside, will grow without bounds as the observer crosses the singularity. And then, as far as we're concerned, well, once you form the singularity, it's game over. None of what you thought was there in the future has a chance to, exist. And well, of course, you also have to modify what's inside the star. So the space-time diagram in the end looks like this, where you have the star collapsing here. That's the stellar surface. That's the center. That's the formation of an outer horizon. And here you have the formation of a null singularity coming from this blue shift, this piling up effect that we talked about. Any questions about that? If you're curious about all of this, I have a problem in the book that I'm not assigning, but you can work through the details. It's not that hard, actually. You can work out the details. You can show that the blue shift effect is exponential, that the fall-off effect that you need to have here to have, a finite amount of energy falling in would be typically a power law. The exponential blue shift will win over the power law fall-off. And you can explore how the energy density behaves and things like that. So it's really a pretty simple exercise. The full back reaction analysis that I did for my PhD was quite a bit more involved in this. But we still did it within a spherically symmetric model, which means that it was tractable. And people after that pursued the more realistic case for a rotating black hole. I'll come to the Kerr solution a little bit later, probably this afternoon. But the point of doing this for Reisner and Nordstrom, while we all knew that it was not astrophysically realistic to talk about charged black holes, we're going to see this afternoon that the causal structure of the pure, unperturbed Kerr solution has a very similar character. So by addressing the instability problem here in a simpler context, we thought that we could make some statements about what's going on in Kerr, what's going on inside a realistic rotating black hole, without all the complications involved in the detailed analysis. And then after that, well, the gaps in the analysis were sort of closed, and I think now we have a pretty good understanding of what's going on. Any questions? Yep, Steve.
In Schwarzschild, the topology of the boundaries, the scry has topology essentially of a cone, S2 cross R1.
Right.
And in Schwarzschild, the singularity also is an S2 cross R1.
Yep.
In Reisner and Nordstrom, scry is the same, but the singularity is just one-dimensional. It's just topologically just R.
Right.
So, big question for me. What's the topology of the null singularity in the mass inflation?
It's still S2 cross R.
S2 cross R?
Yeah, because it has, so in a sense, it's like a cigar, right? It's like a tube. So because it has a finite radius. So metrically, you can actually say quite a bit about the singularity because it's a weaker singularity than what we're used to. So even though the curvature blows up, you can still come up with a chart that produces a finite metric on the singularity. So metrically, you know that there's a finite radius here, and that it extends not so well. The length of time here is a bit problematic, but it extends for at least a finite extension. So I'm not sure if it's infinite or finite, but yeah, so it's S2 cross R.
And of course, another question, more delicate question. What is the nature of I plus there and the way it joins, or does it join topologically to the singularity?
Yeah, so here you get the usual sort of pathology of the map, right? So you have a point here that seems to correspond to crossing of different places, but in fact it's just an artifact of the compactification. That's something we talked about last week. It's a warning sign because you always have to worry about what those points mean, and in fact they're really disjoint in an uncompactified version of this. Okay, I want to make one more comment because it turns out that the singularity formation here that I've just discussed is probably what is saving GR from a very bad embarrassment. So it's not saving itself from all the embarrassments because we still have singularities. And in GR, well, we sort of know that singularities signal the breakdown of the theory. But there's another breakdown of the theory that is even more troubling because it didn't seem to come with the presence of a singularity. That's something I want to describe in the next few minutes before we break for lunch. So I'm going to draw the diagram yet one more time. That's going to be my last time. So suppose we don't take into account all of this stuff. Suppose that we preserve our pure spherical state. We prevent anything from going on outside that would perturb it. We preserve, the pure Reissner-Nordström. So now we have a fixed spacetime. And we look at some test. I'm going to contradict myself, but let's look at a test physical process that we imagine does not perturb the spacetime. So something happens over here. So really what I want to do here is to set up an initial surface where I'm going to place initial conditions, and I want to see what unfolds in the future of that initial surface. So the typical initial value formulation, you say we start at t equals 0 with a given situation. Let's see what happens next. So here I set up my stuff, and I'll even do it all the way over here. Why not? So we place initial data over here, and we watch the future evolution of that initial data. If I'm over here and I'm observing the outcome of the physical process at this point, I see that everything is good. I see that everything is good because if I look backwards in time, and I construct a backwards light cone over here, I see that only what lives inside this light cone could have influenced what's going on at that point. And what lives inside that, and this light cone intersects the initial surface, and therefore, whatever I place here in terms of initial data will uniquely what determines the outcome here. Will uniquely determine the outcome at that point. So what I want to say here is that by drawing this light cone over here, I'm drawing the region of causal contact between this observer at that point and the initial surface. And everything that happens in this wedge here is predicted by what's going on, is predicted as a result of the initial data. So here we imagine that we have a distribution of scalar field, we have a wave equation, we have a nice hyperbolic system. So with a well-posed initial value formulation, we have a well-posed, solution. We have a solution here that depends smoothly on the initial data. So everything I measure here will be determined uniquely by what I placed on the initial surface, and that's what we would expect for a nice behaved spacetime. Let's look at an observer who's up here, beyond the inner horizon. Let's draw the same light cone. Okay, this one, no problem. We still intersect the initial value surface. That one intersects the singularity. And the problem here is that the singularity is completely unpredictable. While in the pure Reissner-Nordström solution, it doesn't do anything, but I don't know that in the physical reality that the singularity would be quiescent. For example, the singularity could decide at random times to emit some stuff. So the singularity at that time could decide, okay, I'm going to emit some burst of radiation because I'm a singularity. The laws of physics don't apply to me. I can do whatever I want. So I'll just emit some burst over here. Or I can emit a burst from here. Or I can do whatever I want. Well, that burst over here was never predicted. And an observer over here, even though would say, okay, most of what occurs here was produced by, by stuff that's controlled from the initial data, a lot is coming from the singularity. And in fact, because I don't control what's going on in the singularity, I cannot for sure say that what occurs over here will be smoothly related to the initial data, for example, that will have, that will be, that what I'm trying to say is that the observer over here, because of the uncontrolled stuff that comes out from the singularity, can never predict completely what's going to happen there. You can predict completely what happens here because you're always in causal contact with the initial surface. Here, you're out of causal contact with the initial surface, or said better, you're in causal contact with stuff you don't control, and that introduces complete unpredictability into what's going to happen in the future of that inner horizon. That's pretty bad, because if you're over here and you stay safe from the singularity, you have to conclude that, well, GR is not predictive. So in this case, it's associated with the presence of a singularity, but in fact, you can come up with concocted spacetimes where you don't have a singularity, but you still have a breakdown in predictability, because in your spacetime, there's a region that is now basically out of the domain of dependence of your initial value surface. Those spacetimes are said to have Cauchy horizons. And we have a breakdown of the Cauchy problem, which is really saying that you have a breakdown in predictability, with or without the singularity. So if I have a singularity, well, and I might be upset by the presence of the singularity, but even in Schwarzschild spacetime, for example, I know that predictability is broken down right at the singularity. But before you hit the singularity, everything is fine and dandy. You can predict anything up to that point. In Schwarzschild, you're always in causal contact, with the initial value surface. So there's never any breakdown of predictability so long as you avoid the singularity. So it's only at the last moment where you give up hope. Here, you're in a place where everything is very mild. There's really nothing here that blows up. There's really nothing there that suggests that you should be in a pathological situation. It's just that, but now you have to account for the fact that this singularity, can have an arbitrary influence on the development of the solution beyond this wedge over here, which is what I mean by the Cauchy horizon. So this breakdown of predictability inside Reissner-Nordström in other spacetimes, including Kerr, was a very troubling thing. And there's a very different character to this breakdown from the one that we get from the singularity. If all my physical fields blow up and I know that my theory is breaking down, I certainly would expect a breakdown in predictability. But if all my physical fields, including the curvature, including whatever is going on with the scalar field, including the velocity of light rays, including anything, if nothing here suggests a breaking down of anything in terms of the laws of physics, but I still get a breakdown in predictability, then I'm troubled, because I would like to be safeguarded against this. I would like my theory to protect itself against breakdowns of predictability. I would like the theory to be better than that. Well, the key seems to be that Cauchy horizons tend to be unstable. They tend to generate instabilities. And here's an example where, in fact, if you take into account those instabilities, you find that, well, those spacetimes here where you make sure, those spacetimes over here where you prevent perturbations from existing are a very small set. In fact, they're a set of measure zero of all possible spacetimes. As soon as you relax, the assumption of no perturbation, you find that you generate an instability. And the instability has the character of transforming the Cauchy horizon into a singularity. And therefore, here's a place where you expect breakdown of predictability because you have a physical singularity present there. And it's the same situation. Before you hit the singularity, everything is fine, everything is predictable. And it's only as you hit the singularity itself that predictability is lost, along with the formulation of the laws of physics, because, well, we know that ultimately we need something better to describe what's going on there. This situation over here is really troubling because, again, we get a breakdown of predictability without direct causes. It's a very troubling thing, but there are lots of examples in GR where this seems to occur. But as far as I know, in many of those examples, if not all of them, there are reasons to believe that those Cauchy horizons that you develop are pathological in the sense that they end up being unstable against external perturbations. For example, I'm not sure if there's an actual theorem that says that. I think there's a conjecture that says that. I think it's still very much a conjecture, in fact, because that's what cosmic censorship is all about. The strong form of cosmic censorship is to protect ourselves against Cauchy horizons, and we're still chasing after that. We're still chasing after the weak form of cosmic censorship, the one that says that singularities can still exist but be enclosed within event horizons. That's a stronger form. It says that no singularity can be time-like, because if you had the time-like singularity, you would necessarily produce a breakdown in, you would necessarily produce a Cauchy horizon. You would necessarily produce a breakdown in predictability. And that is, well, again, that's something that we would like the theory to be able to rule out. And if someone ever proves cosmic censorship, well, that's what it's going to mean. It's going to mean that we have, protection against the breakdown of the Cauchy problem in GR. All right, any questions? You're all stunned. All right, so we can break here, and we'll come back this afternoon. And this afternoon, I'll do Kerr. I won't do a lot with Kerr. I'll just do the essentials of Kerr, and I'll draw diagrams for Kerr that will look an awful lot like this. So all of this that I'm talking about here has also a correspondence in Kerr. But then in the afternoon, I'll start talking about black hole properties that are not dependent on particular solutions, and we'll go into a more sort of formal development of black hole theory based on very simple ideas like the existence of killing vectors and things like that. So, and if you have other questions, if questions emerge during your lunch break, we can certainly talk about that this afternoon. All right.